Hey darts fans, that's Timo Newman here, the transporter. Welcome to the good ship Undarted Waters. We're on this voyage, long and potentially perilous, but it's the physics of dart flight. What is the physics underlying the trajectory of darts? Some funny physics was going on there. My 180 turned out to be a 45, never mind. But this is actually a remake of part 2 of this series. I made a video on this topic a couple of days ago. It was too long, it was too technical. I put it online with a heavy heart and asked for feedback, and the feedback was really helpful, saying it's okay but it's a bit dry, because we've got some folks who want to get into the really technical details, but probably most folks just want to get the concepts so that they can see what the big picture is. So what I'll be doing now with this series is, if there are technical details, I will record those in separate videos which are labeled like heavy maths or something. But any important ideas will be presented in videos like today's video, which do not have any maths at all. Because as Richard Feynman said, the great American Nobel laureate physicist from the 20th century, sort of active in the between the Second World War and the 1980s, as Richard Feynman said, if you can't explain it to someone who doesn't know any maths, then you don't understand it. Physics does not need maths in order to be explained, okay? So what I'll do today is a brief recap of how we set up this problem in the first part of this series. And then what we're going to do is take a trip to outer space and think about how a dart would fly through, not the air because there's no air in space, how it would fly through the vacuum if there were no forces acting on it. And that will be really helpful to get two very important concepts across, and we'll need both of those concepts in the next video when we add gravity. We come back down to Earth and add gravity. So let me just turn off the board light here, get the old whiteboard, and hopefully everyone can see that clearly. Right, so this is just to remind everyone what the setup was, and I've flipped the diagram from the first video, and I've also tried to make this dart player kind of relatively normal size, because I think he was about 7'6" in the first picture. But one of the key points of this series is that not only are we going to learn about how a dart goes through its trajectory, but we're going to learn how we can personalize that to each unique individual dart player, because the parameters that you have to specify in order to talk about a trajectory of a dart, some of those are unique to every player. And let's just see how that works on here. So one parameter is the height of the elbow just at the point of release of the dart. So that's going to be unique to every player. And also the distance horizontally from the elbow to the dartboard. And these are parameters that you can get a friend or family member to measure for you. Just kind of pretend to go through your throw, kind of freeze your throw where you'd release the dart, and get the family member to measure where your elbow is with respect to the ground and with respect to the board. Okay, because we need those parameters. We also need to know, this is just a magnified view of the arm here. We also need to know the forearm length. And by forearm, I mean the distance from the tip of the elbow to the dart. And we're calling that L. And we're just establishing a bit of notation. So L, length of the forearm. HT is the height of the target that you're aiming for. In this case, it's the treble 20. HE is the height of the elbow, and little d is the distance from your elbow horizontally to the board. Okay? And then there's two more symbols on this. U is the speed of the dart when it's released from the hand. All right, that's an important variable. It's not something that we can measure, but we need that in our formulation, and it's something that we can actually get out of the theory once we've developed it. Okay. And the final thing is, just again, this magnified view, what is the angle of the release of the dart from the horizontal? And assuming there's no significant wrist movement, and I know that is an approximation at this point, but we can add that in later if we need to, but that will also be the same as the angle between the forearm and the vertical. Okay, so basically releasing a dart, this angle to the horizontal similar to the angle of my forearm relative to the vertical. So that's just a recap of how we set up the problem. And here's a typical trajectory of the dart happily going into the treble 20 bed from our friend the matchstick man here, who's apparently a very good darts player and can alter his height at will, which is pretty impressive. So what are these two important concepts that I want to talk about today? Well, before I get to them, they're not to do with the forces. Okay, as I explained in the first video, there are two forces acting on this dart, but I want to remove the forces. That's why we're talking about going to outer space, so that we can clear our mind of forces and just think about two other things that are very, very important to this problem. So let me just remind you what those forces are, and then I'll explain why they're absent when we go to outer space. Let's do a magnified view of the dart here, and let's say it's in the middle of its flight somewhere. So the dart is traveling on its trajectory. So there's kind of the dart there. All right. And it's going in this direction. So what are the two forces acting on this dart? The most important force that's acting on it is a downward force due to gravity. Okay, and I'll talk much more about that in the next video. But that's a force that's vertically downward. And the other force is the air resistance. The dart is moving through this fluid, low density fluid that we call air, and that is basically tugging the dart in the opposite direction of travel. And so that there, we'll just call that air resistance here. So we're going to add gravity back, and we'll pretend we're playing on Earth in a vacuum, so we don't have to worry about air resistance, because that's a really horrible thing to have to add into the theory. It's very complicated. And then finally we will play on Earth in air and add air resistance as well, and we'll see how that changes things. But the most important thing, to be honest, in terms of forces is gravity itself. But these two concepts I want to get to don't depend on the forces. So let's get rid of the forces, and let's say that this dart is moving with no forces acting on it whatsoever. Okay? And that would be true in outer space, where you're in a vacuum and you're also away from any large like planets or stars, which are large gravitational sort of centers. Basically in outer space, very weak gravitational field. So I'm going to take all this away, and I'm going to have to change this picture a bit, because if he throws the dart in that direction in outer space, it's not going to go anywhere near the dartboard, as we'll see. So his arm is going to have to be a lot further forward when he releases the dart, as we shall see shortly. Okay. So let's start with the first concept. And this comes from Isaac Newton. So Isaac Newton is considered by many as the greatest physicist of all time, even greater than Albert Einstein. Einstein had a portrait of Newton on the wall behind his desk. He revered Isaac Newton. And Isaac Newton was a man that was born in Lincolnshire. He lived most of his life in Cambridge, where he was a scholar. And he was active in the late 1600s and early 1700s. And he created many things in science, but he's famous in particular for his laws of motion, and also actually his law of gravity, and we'll be using his gravity law in the next video. But he wrote down 3 laws of motion which are used to this day in physics and engineering to describe how things move. And the concept I want to get across today is what is Newton's first law of motion, and it's the following statement. That if you have an object that is experiencing no forces, then its velocity is constant. So let's write that down. This is Newton's first law of motion, let's call it N1, that if there are no forces, then the velocity is a constant. Okay? And if the velocity happens to be zero, if an object is at rest, it means it will continue at rest if there are no forces acting on it. But if it's moving with a constant velocity and there are no forces acting on it, it will continue moving at a constant velocity. Now you might say, well, hang on, the Earth goes round the Sun at a constant speed, but it has a force acting on it, which is the force of attraction of gravity from the Sun. And that's absolutely true. Newton's first law is not that the speed is constant, it's that the velocity is constant. And you remember I said that the velocity is something which has a, if that's the velocity, it has a size, which we call the speed, but it also crucially has a direction. And indeed, the Earth has a force acting on it from the Sun of gravitational attraction. And as you know, the Earth goes round, it orbits the Sun, and it's constantly changing its direction. Its velocity is constantly changing round, and so its velocity is not constant. The speed is approximately constant, but not the velocity. If the Sun were to suddenly disappear, the Earth at that instant would just go in a straight line. Its velocity at that instant when the Sun disappears would then be the velocity the Earth has forevermore, unless it goes near any other large object and gets a gravitational force again. Okay. So if we're playing darts in outer space, what this means is that the moment the dart leaves the player's hand, it will travel in a straight line. And so in order to hit the target, you have to have the angle of release absolutely perfect. And doesn't matter how fast you throw, the speed is irrelevant because the dart's just going to travel in a straight line. So how would that look on this diagram then? You'd have to throw the dart at a very, very small angle, like that. So the angle to the horizontal is really, really tiny in this case. But that dart will travel in a completely straight line to the target. And what you can do is actually calculate what that angle is for a given player, depending on all of their parameters. If you had a much, let me just sort of draw a ghost player who's also playing. Okay, so here's a ghost player playing. Whoops, the arm has to come from the shoulder like that. So this player has to throw the dart at quite a steep angle to get to the target. Okay, but again, it will be a perfectly straight line. So the angle that the dart has to be thrown depends on all of these parameters of the dart player's stance, their action, their height, and all of those kinds of things. Okay, but it will travel in a straight line, and that's because of Newton's first law. Now, you might say, okay, Timo, but we don't play darts in outer space. We play darts on Earth, and you've already told us that there are forces acting on the dart on Earth, so Newton's first law won't apply. So why do we care about this velocity being constant? And that's a really good point, but we do need to care. And that's because of the second concept I want to get across, which is really absolutely central to understanding projectiles, including darts and whatever else you want to think about, tennis balls, ping pong balls, cannonballs, any ballistic object that you might want to think about. What is the second concept? And this is really, really important. Okay. let's do a magnified view of this dart again. Okay. And it's got some velocity. Okay. Now, I want to represent this velocity by a line. And the line tells us, that green line tells us what the direction of the velocity is. And I also want the length of that green line to tell me the speed. And this is something that we call a vector. A vector is just a way to represent something if it has a size and a direction. So a force or a velocity is something in science which has a size and it also has a direction. If I push on something, okay, can you see that if I push on something, you can say, well, what direction is Timo pushing? And also, how hard is Timo pushing? Okay, and so like a force or a velocity has a size and a direction. And the way we represent that is we draw a line with an arrow, and the length of the line tells us the size, and the direction of the line tells us the direction of the vector. Okay, so this is the velocity, and the length of that line would be the speed of that dart u. But here's this really amazing thing, this really important thing, is that, as we'll see when we talk about gravity, we'll go into more detail on this, but the physics applies independently to the vertical direction of the velocity and the horizontal direction. If that were not true, physics would kind of be impossible, but that's the way the universe is, that it kind of gives us a break, us poor humans. It says, well, I'll tell you what, we live in 3 dimensions, but I'll let you write down your theories of physics where you can actually write equations down for what happens in the vertical direction, what happens in the horizontal direction, and say if we were talking about cricket where a ball might swing, you'd also worry about the 3rd dimension as well that's coming out of the board, but we don't have to really worry about that in darts, you know? So this means then that we need to think about the vertical and the horizontal, all right? And we can say that this velocity has a piece that is vertical and it has a piece that is horizontal, all right? And this is absolutely critical because, I'll give you kind of a spoiler for the next video. Remember I said that gravity acts downwards. So here's this incredible thing that when you throw a dart, the dart only feels a force in the vertical direction if you don't worry about the air resistance for a moment. It's just gravity is pulling it vertically downward. That means that Newton's first law applies to the horizontal direction. That the horizontal speed, if you like, stays constant. So the length of this horizontal piece of the velocity, you could call that the, well, let's just write it as horizontal, let's call it the component, the horizontal component of the velocity. And then this vertical line we can call the vertical component of the velocity. Okay, but here's, this might seem a bit dry, but this is really deep and really important and actually really cool. And you might even think, I don't believe it, but it really is the case. That because we can break it into these 2 pieces, the horizontal piece that does not experience any force will just continue. Okay, so let me give you an example of this. If you think about a sad subject, but let's say a World War II bomber, so a plane that's going to be dropping bombs, it's a horrible thing. Well, actually, let's think about it as a plane that's dropping aid packages in Africa during a famine. How about that? So a plane is traveling and it drops a package. Let's draw that. Okay, I just dropped a pen, but that's not helpful to what we're talking about here. So here's a plane. Okay, and it's flying in this direction. So here it is a bit later on. And it has this box that it drops here, which is full of rice, okay, and bandages. Okay, it's a very useful thing. And the question is, what happens to that box once it's left the plane? Okay, well, the plane is experiencing gravity, of course, but it also has lift from the wings, so it's traveling in a horizontal direction. But once the box leaves the plane, the box has no lift. It's just going to fall, right? Fall downwards. So you might think that the box falls to the ground, but it really doesn't. And why doesn't it? Because when it left the plane, it was traveling with this horizontal component of the velocity. So actually, this box is going to stay underneath the plane as it drops. Okay, so if the plane was over here, then when it finally sort of leaves the whiteboard, the box, whoops, the box is red. The box stays underneath the plane because that horizontal component of the velocity is just going to stay the same because there's no forces acting on it. Newton's first law. In the absence of forces, the velocity is a constant, and we can break that velocity into vertical and horizontal pieces. Really deep concept. So in the horizontal direction, no forces, therefore that box will just continue at the same horizontal speed. Okay, but because it's going to accelerate in the vertical direction, it will make this kind of shape, but it will stay underneath the plane. And I remember as a teenager learning that in physics, and I just didn't believe it. And my physics teacher got quite annoyed with me that I didn't see this, but it just didn't feel right to me. But you can find video footage, I think, on YouTube of bombs being dropped from planes during World War II, and they're dropped and they just fall down vertically from the point of view of the plane. The camera's on the plane. The object stays underneath the plane, and that's because of Newton's first law. The horizontal component experiencing no forces just continues along. Really beautiful stuff. So just as a final word today, we're not doing any maths in this video, but in case anyone's curious, if they were playing darts in outer space, what angles would they need to throw their dart to go, say, from double three up to double tops? What's the range of angles? I worked out mine based on my own values for height of elbow and all that. And mine go from -5 degrees to 4.5 degrees. But if you want to work out your own, I'm going to show you the formula you'd need to use. You can get a pocket calculator and just put this horrible thing into your pocket calculator, okay? I'm sorry about that glaring light there. But can you see that? That's the distance of your elbow from the target. That's the height of the target. That's the height of your elbow above the ground. And that's the length of your forearm. And this is a square root symbol. So if you are curious, you can measure these, your elbow height and all the rest of those parameters that I've talked about, and plug them into this formula. And as you vary the height of the target from the height of a double three up to the height of tops, this will give you the slope, tell you the different slopes that you need for hitting those targets. All right. Okay, so that's us then for today. Hopefully a shorter video and less dry than the terrible attempt that I made before. Some folks did actually have the courage to watch that. I think some of them are still convalescing. Kudos to them for sitting through that, but hopefully this is a better style, and we'll continue in the next video with adding gravity back down to Earth. So 3 darts at the oche, make them count, and I'll see you next time.